one here, it's a little more crowded. Why don't I remove some of these marks that we have here? And now, the last one of these sorts of this type of structure that we want to consider is pyridine. How about a green square here? Rectangle, I guess it is. So we've seen pyridine a number of times. We've used it as a base in all sorts of reactions, like when we were making acyl chlorides the other day. I wanted to ask, is pyridine an aromatic compound? So let's take the same approach. We'll stick with the green here. Is it cyclic? Looks like it is. Is it planar? We're going to assume that it is. Is it conjugated? This is where now we have to look and see what sorts of electrons could be involved in the conjugated system. So here, using the structure of pyridine shown in the green rectangle, the carbons are pretty easy. We know all of these carbons are sp2 hybridized. They have a p orbital to form the double bond, 2 through 6. But now, how about the nitrogen? What you'll notice is that the nitrogen is also involved in a double bond. We could write resonance structures of this. So in order to participate in that pi bond, the nitrogen then also has to be sp2 hybridized. And that's what's shown down here on the bottom. We can use the one on the left with these bluish colored orbitals. So notice all of these carbons are sp2 hybridized. They have a p orbital. And then for the nitrogen to participate in that double bond, it also is sp2 hybridized. So that means the system is conjugated. And just to highlight it, so that's this orbital here that I'm circling. Okay, so it has electrons that could be involved in the pi system. Now, last is where we have to make these decisions about 4n plus 2. Question mark. So let's count up the electrons again. So on the carbons, I'll go back to the green rectangle. We have 2 4 electrons. And then it looks like this carbon-nitrogen double bond, those are both with a p orbital. So that's going to give us 6 pi electrons. So once again, so 2 here between carbons 2 and 3. So 2, 4, 6 pi electrons. But now, what about this lone pair on the nitrogen? So just like we saw with the oxygen in the previous case, now only if the p orbital is occupied by the electrons now in this double bond, this lone pair is not going to be part of the conjugated system. So before we had one lone pair on the oxygen being involved in the conjugated system. Now the nitrogen, it's already involved in this double bond. And that can be seen again down in this orbital picture below. That means these 2 electrons in this lone pair are pointing off perpendicular to the ring in an sp2 hybridized orbital. So they're not going to contribute to aromaticity. They're not part of the pi system or the p orbitals. And that's what these different depictions all down below are showing. Maybe the one on the right is the easiest one to see here. So that lone pair is just pointing off here to the right in this sp2 hybridized orbital, perpendicular to the pi system. So we're not going to account those in our accounting here for Huckel's rule. So for pyridine, it'll be, again, 2, back to the green box, 2, 4, 6 pi electrons. The lone pair doesn't count. So then 6 is where n equals 1. So this compound will be aromatic. So a couple of different variations. The simplest case is with benzene. And then now we can think about having anions and cations. And now with these heteroatoms, you have a couple of different scenarios. One is this case where you have something like this pyrrole here, where we have to consider including the lone pair and see what that gives us in terms of the number of electrons. You have a case like furan and thiophene, the next 2 compounds to the right, where only one of those 2 lone pairs of electrons could be contributing to the conjugated system. The other one's pointing off perpendicularly in an sp2 hybridized orbital. Or the last scenario, with pyridine, where the p orbital are already occupied by this carbon-nitrogen double bond. So there the lone pair is pointing off perpendicularly in an sp2 hybridized orbital. So different varieties of doing our accounting, but all pretty much the same idea. Okay, so I think I'll post some practice problems so we have to decide if those compounds are aromatic or not. And then this was also shown in the videos, trying to have everyone be really excited about this idea of aromaticity, because this is not some arbitrary or esoteric concept. You end up finding aromatic compounds everywhere, and in particular in biology. So as I mentioned, that of these aromatic compounds, this indole, this imidazole, these are aromatic compounds. This is the side chain indole of tryptophan, the amino acid. This is histidine for the imidazole. And then all of the nucleobases, are the common nucleobases in DNA and RNA, are aromatic as well. So purine here is the basis of adenosine and guanosine, and the pyrimidine is the basis of cytidine, uridine, and thymidine. So you end up seeing a lot of these aromatic compounds in biology or biochemistry, and actually we can think more about how these contribute to the structure of things like DNA as well. It has to deal a lot with the aromatic chemistry. But we'll save that for another day. Okay, so then the last thing, as we're flipping around all of these slides, where I need to go back and find where I showed the anti-aromatic compound. It was this one here. And this one, yesterday, I struggled and I drew the 8-membered ring. That's a little easier than 7. Just imagine the stop sign here. So we'll stick with that. I left it there so I don't have to try it again. Now, let's take the same approach that we've been seeing all along and ask, is the compound aromatic or not? I'll write it down here on the side since it's a little bit more room. Is it cyclic? So it is. It might not look like it the way it's drawn, but it's supposed to be here. And is it planar? And this gets back to James's question earlier, is we're just going to assume yes. And I mentioned assume because this is actually wrong, but we're going to assume it's planar. Maybe someone can try that on an exam. You write down, well, it's not the right answer. Well, I assumed that you wanted the incorrect answer. Yes, and so we'll see. But here, planar, we're going to assume it's planar. And then, is it conjugated? Here, that's what that scribbles there. So we need to have a continuous system of p orbitals. And so here, each of these carbons, they are all sp2 hybridized. We don't have to worry about oxygen, nitrogen, and sulfur now. So this would make it look like it's conjugated. This one's also wrong, but we'll come back to that in a second. And then we want to ask, does it meet the 4n+2 rule for Huckel's rule? So now if we count up the electrons, let's just start over here in the upper left. We have 2, 4, 6, 8 pi electrons. So this is a case actually where it doesn't meet 4n+2. Instead, it would meet 4n for the number of pi electrons. So if n equals 2, this would be a case where you have 8 pi electrons overall. So that would mean something then is actually anti-aromatic. So what this means now in this particular case is that you end up having this very electron-rich compound, all these electrons here in these pi bonds. However, it's not able to gain or harness that resonance stabilization. And indeed, it would be something that would be at first considered anti-aromatic. And what ends up oftentimes happening, and this is why the planarity is difficult to see, for example, is that this is so energetically unfavorable that the compound will likely assume some other, maybe a non-planar arrangement, or even not being conjugated, just to try to have those electrons as far away from each other as possible. So what actually happens with this compound, this cyclooctatetraene, is rather than just being flat, it actually forms this bent shape that's shown here in the middle. So because it's not getting aromatic stabilization, it actually is not planar. And that's why what I said earlier was wrong about assuming it's planar. And that actually breaks up the conjugation as well. So a lot of times a compound, if it actually looks at first like it might be anti-aromatic, that's so energetically unfavorable that the structure will try to adopt a conformation that gets the electron density as far away from each other as possible. Now, there are cases where maybe the structure doesn't have that flexibility, and then it would be what's known as the anti-aromatic compound. So with Crystal, you can address the the approach in different ways. I presented it like this because, like, if it's not cyclic, you can just stop immediately. The planarity, we kind of have to assume it's planar, and then the conjugated has those more difficult that more difficult analysis that we have to do. But a lot of times, you could first look at the electron pairs and see, do I have something that's 4n or 4n plus 2? So that certainly follows. Okay. So yes, as Lorianne asked, so anti-aromatic is basically the same as aromatic, but meets 4n and 4n plus 2. Yes, and so generally what ends up happening is that we kind of didn't cover the formal definition of anti-aromatic. We can use the definition that you had just given for now, is that a compound that meets all of the criteria of aromatic, so cyclic, planar, conjugated, but meets 4n, is one that we'll call anti-aromatic. The real definition is you actually end up comparing something that's not cyclic, like this compound here, this triene, versus the cyclic form in the energy, say plus H2. And you look and see this compound, everything is the same except one is cyclic and one is not, and we've lost hydrogen. And you look and see this meets these other all the criteria, and is this more stable than this one? And then, or is it less stable? That would give you the definition of aromatic versus anti-aromatic. But for what our purposes now, we're going to take this stepwise approach shown here on the left as well. Okay, and so then Crystal asked, so yes, I think it's a great point, and this is a complication at times. So what we're doing here is, a lot of the times the compounds that we'll be working with, we'll see that they're going to be aromatic, benzene and so on here, and these other compounds that we've seen. There are other compounds now that are known as being anti-aromatic, such as, and then an anti-aromatic would be a compound that meets all of these criteria, except, like you had mentioned, that the number of electrons in the pi system is the 4n, not 4n plus 2. Okay, so on paper, then we could then say that compound is actually, it's anti-aromatic based on those definitions. Okay, so that's the next step. However, in reality, if a compound is defined then as anti-aromatic, that is usually so energetically unfavorable that maybe there's a structure it can adopt that tries to move those electrons as far away from each other as possible. And this cyclooctatetraene is a good example of that. And so in this particular case, it actually is going to break planarity and adopt this particular non-planar conformation that's not conjugated. So in the end, it technically is not aromatic according to our definitions, but you wouldn't know that unless you could observe the structure itself. So that's the confusing part. So if we just assume things are planar, if for right now, to describe the concept, then this compound here would be the cyclooctatetraene I'm highlighting, would fit the definition of anti-aromatic. However, because things are much more complicated, that in reality, it actually breaks planarity and conjugation because being anti-aromatic would be so unfavorable. So in reality, actually, it's not aromatic. So it goes one step then beyond defining anti versus aromatic. Okay,